here's something kind of neat. We know that electric fields cause forces to be felt by charges that are in those electric fields. But forces cause particles to accelerate, right? Which means that particles in electric fields have, kinematic motion, right? They follow the same rules, like the laundry list rules that we talked about for, masses in gravitational fields, because just like gravitational fields accelerate masses, electric fields will accelerate charges. Kind of cool. So how can we merge those two worlds? How can we bring the world of kinematics that we learned last semester into this world of electrostatics that we're learning right now? And I'm going to show you, and it's kind of neat, and it's going to make you feel like, wow, like this is all coming together, and I actually learned something last semester. Okay, so let's suppose that I have a battery. Okay, by the way, that's a symbol for a battery. And it's connected to two plates, right? So actually, this is going to be the negative side of the battery. And this is going to be the positive side of the battery. Okay, so this battery is connected to two plates. And so I'm getting a whole bunch of negative charges here. So this is a negative plate. I'm getting a whole bunch of positive charges here, and this is a positive plate. That's how a battery works. If the positive side of the battery will give two plates. This is actually called a capacitor. Two parallel plates separated by a certain distance is called a capacitor. And you'll have the positive side of the battery giving a positive side to the capacitor, and the negative side of the battery giving a negative side to the capacitor. Okay? And so let's say that I have one charge that's floating right up here. We're holding this charge there, because remember, it's negative and this plate is negative, so it does not like that. It creates a force in this direction, right? And we know that force equals ma, right? So this question here is asking us, with what speed and kinetic energy does it acquire while traveling the 1 centimeter, so this distance here is 0.01 meters, the 1 centimeter from the top of the plate to the bottom of the plate. Okay? All right. This is essentially a kinematics question, right? If we're going to find the speed down there, we need to find v2. So we need to do a laundry list. Let's do a laundry list. Some of you might be like, oh, yeah, familiar. Some of you might be like, oh, no, I thought I left 130 behind. Well, I'm sorry, but it's going to be like riding a bike. I promise. You're going to do this, and it's going to be like, I remember. Okay, so v1, we're releasing this from rest, right? And because there is this force, this electric force, just like, if you drop something, gravity pulls a mass down, electric force is going to pull this charge down, okay? So you're going to get some velocity on the other side. What is our acceleration? We don't know that either because, well, we just don't, right? The distance we know, it's 0.01, and we also don't know how long it took, right? Now, this is what we're looking for. And I'm going to guess it's going to be easier to find our acceleration than it is going to be able to find our time. And I'm going to show you why. Because here's what we know. We know that this is an electric force, right? An electric force equals the electric field times the charge, right? But any force is also equal to the mass times the acceleration. This means we could very easily find the acceleration of this charge in this electric field by solving for A. So it would just be EQ over M. Electric field strength, right? And incidentally, just to show you guys here, this will go to here, this will go here, this will go here, this will go here, right? The electric fields always point from positive to negative charges, and negative charges move against electric field lines. All right, so what is this acceleration? Well, the problem, luckily, tells us what our electric field is. Electric field is 1 times 10 to the 4 newtons per coulomb. That's easy, okay? I told you that this is an electron, so we obviously know that the charge is 1.6 times 10 to the minus 19. That's easy. And the mass of an electron, we learned, is 9.1 times 10 to the minus 31. So finding this acceleration is really easy. It's just plugging in the stuff that we're given and what we already know about an electron. I get an acceleration when I do this problem of, what kind of acceleration do I get? Let's see here. Yes, I get an acceleration of, it's pretty massive, 1.75 times 10 to the 15. All right, once again, why should it be so big? It should be so big because we have a really small mass and a fairly large electric field, right? You're going to have a decent acceleration, especially when something is this low in mass. It's just that minus 31 covers a lot of ground. All right, so that helps us out a lot. We know that the acceleration of this electron is going to be 1.75 times 10 to the 15 meters per second squared. All right, so how would we go about finding V2 then if we have V1, V2, A, and D? Well, you all did very nicely with your kinematics last semester. So you would remember that there was a formula that looks something like V2 squared equals V1 squared plus 2AD, right? V1 squared is 0, so then that's just 2 times 1.75 times 10 to the 15 times the distance, which is 0.01, right? And to find V2, we have to take the square root, so it's the square root of all that. I get an answer of 4.2 times 10 to the 6th meters per second. That's awesome. I like that answer. You know why I like that answer? Because it's not quite the speed of light. What's the speed of light? The speed of light is 3 times 10 to the 8th. If you're ever doing a velocity problem involving small particles where the velocities are very, very high, this can't be bigger than an 8. If this is bigger than an 8, you've made a mistake somewhere. So for example, if this were bigger than an 8, it means that very likely you didn't take the square root. So just something to look out for. So, but that's reasonable. It's super fast, but it's not past the speed of light. And Einstein's theory of relativity says we can never have a velocity faster than the speed of light. So what do we do? Next, it says, what is the speed and kinetic energy? I'm not going to solve for kinetic energy. You just put that into kinetic energy equals 1/2 mv squared. You can solve for that very easily. I'm not going to waste the limited space on this glass right now. But I do want to answer the question then of how long does it take to travel this distance? So now we're solving for t, right? All right, so now we know that V2 is actually 4.2 times 10 to the 6th meters per second. All we have to do is use another kinematics equation, one that you know very well, to solve for this t. I'll give you a second to think about it. And hopefully the answer that you came up is V2 equals V1 plus AT. Right, because now I can just take my V2 here, my 4.2 times 10 to the 6th equals, that's 0, right? My acceleration is 1.75 times 10 to the 15 meters per second squared times t, which means my t must be, I get an answer of 2.4 times 10 to the minus 9 seconds. Wow, that's really small. It's really fast. I mean, we're talking like 2.5 nanoseconds, right? Why so small? Because if this were accelerating for much longer than that, this velocity would exceed the speed of light and we would have a problem. So can't do that. All right. That is how we combined this new world that we just learned about with our old world of kinematics. And hope that was interesting. I'll see you in the next video for the Why Do We Care finale.